On Friday, we looked at conservation of energy involving charges. It was a lot like conservation of energy involving masses. When a mass, like a car for instance, accelerates or decelerates through a gravitational field, we end up analyzing it as an EI equals EF problem, right? Potential energy equals kinetic energy, or kinetic equals potential, depends on which way it's going. We do the same thing when we're talking about electric charges, when they're accelerating or decelerating through an electric field. In fact, they're so similar that we think of the electric field as the gravitational field, and we think of the charged particle that's accelerating through that electric field as the car that's either accelerating or decelerating through the gravitational field. For instance, if I have a charged particle that is speeding up as it's going from one plate to another plate, or as it's speeding up as it's going through this electric field, I visualize that in my head as a car going down a hill, accelerating down a hill. If I have a charged particle that's slowing down in that electric field, I visualize that as the car going up the hill, as the car slows down when it goes up the hill. The beauty of that is that I can see the car. I can see the car in my mind going down the hill or up the hill. I know that if a car starts at rest at the top of a hill, I know that it's got only potential energy, MGH. As the car accelerates down the hill, I know that potential is converted to kinetic energy. I know the potential decreases, the kinetic energy increases. I know when it gets to the bottom, I'm left with only kinetic energy. I know that if the car doesn't start at rest at the top of the hill, if it's moving at the beginning, the top of the hill, then I know it starts with kinetic end potential. And I know that if I'm not trying to find the speed of the car at the bottom of the hill, but rather partway down the hill, then I know that I've got potential at the end of the problem as well. Now, if I'm visualizing a charged particle speeding up as this car speeding up as it goes down the hill, I'm going to do the exact same thing as I have right here, except that MGH is going to be swapped out and QV is going to be swapped in. So picture the car going down the hill. Wherever you have MGH, gravitational potential energy, just replace it with electric potential energy, QV, and then solve it the way you'd solve a gravity problem. Okay, if we can do that in Physics 20 with MGH, there's no reason why we can't do it in Physics 30 with Q times V. It's the same thing except for those two variables, QV. Does that kind of make sense? We're going to get right into checking the homework here. And then we'll do another example with a couple more problems to illustrate this even further here. The homework that we had over the weekend, there was only two problems there. It was page 571. Practice problems on page 571. I think there was two of them. So let's take a look at those two problems on page 571 now. I want to do at least one of these, whether you guys think you need them gone over or not. I want to do at least one of them. Okay? If you need both of them gone over, then that's fine. We'll do both of them. Which one or ones would you guys like to go over? Number two? Are we okay with number one, or do we want number one as well? Number one as well? Okay. Number one and number two. All right. Let's look at the problems. Let's read them, and let's see if we can turn them into a more straightforward question that we're familiar with from Physics 20. A negative charge is at rest, starts at rest, at a position in the electric field of a larger positive charge, has this much potential energy. When it's released, it accelerates. So you've got a charged particle that's not moving, but then as it's released, it accelerates. I see that in my head right now, as I speak to you right now. I see that car at the top of the hill being released, starting to accelerate down the hill. If I visualize it that way, then tell me what kind of energy that car is going to have before it's released, or as it's released. Potential energy, right. It's got MGH. It's got no kinetic because it started at rest. Now, I want to find the kinetic energy when it gets to the larger charge. In other words, if I'm picturing this as the car again, I want to find the kinetic energy when it hits the ground, when it gets to the bottom level, okay, to the base of the hill. What kind of energy does it have when it gets to the bottom? Kinetic energy. It's going to be 1/2 mv squared, right? Now, what I want to do here now is replace MGH with QV. I thought of it as MGH, but now I'm replacing it with QV because I know it's always, in electricity, going to be QV. Now I want to start plugging some numbers in. We're told here Not that we do have a charge there. We're told what the value of the charge is, but we don't need that value of charge. We don't know what the potential is here. But guys, look at what they're trying to do us a favor in this question. Look at what we do have. We're told the initial, that tongue twister, I can't say it, that the initial potential energy is 3.2 times 10 to the negative 12. I don't need to multiply these two numbers together even if I had them. They're telling me what the product of those two numbers are already. It's 3.2 times 10 to the minus 12. If you don't know what that potential energy is already, and you do know the value of Q and V, then multiply them. But why bother multiplying two numbers together when you don't even know one of them to get a number that you already have? Okay, we have that potential energy already. Now we're looking for the kinetic energy as it reaches the bottom or as it reaches the other charge. I don't need this either. Yeah, I know that 1/2 mv squared is kinetic energy, so let's just say the potential energy is this, the kinetic energy is this. What am I looking for? The kinetic energy when it reaches the other charge? What's the answer? 3.2 times 10 to the minus 19. Some of you wouldn't have even done any math here. Some of you wouldn't have even set up an equation. Some of you would have said, look, I know that if it starts off with this much potential, it must end up with this much kinetic. And if you can recognize that without writing anything like this down, then that's great. That's fine. If you can't, though, you can see that by going by this method there, this EI equals EF, it still works out. We just don't do it in the typical way. We just don't multiply QV and 1/2 mv squared because we already have that value. Is that okay? Take a look at the second one. I think it was similar, actually. A small sphere with a charge of minus 2 microcoulombs accelerates from rest, speeds up from rest. A car sitting at the top of the hill speeds up as it goes down the hill. Yep. Okay, back to the first one for a second. Go ahead.
For the answer.
Sorry, yes. It should be 10 to the negative 12, yeah. Yeah, it came from this, right? I just misread that, that's all. Yeah, thank you. So it accelerates from rest. It's like a car accelerating from rest at the top of a hill going down the hill. Again, we're going to say EI equals EF because that's what we do whenever a charge speeds up. At the top of the hill, the car has potential energy. At the bottom of the hill, the car has kinetic energy. We're going to sub in QV wherever we see MGH. A lot of you aren't even going to write down MGH, right? Lots of you are just going to skip that step and go straight to QV equals 1/2 mv squared, and that's fine. You don't have to write down MGH, but think of it in your head. Do the substitution in your head if you want. What do we got here? We've got the charge. We've got the mass. We've got the final speed. And we want to find out how much potential energy the negative charge lost. Well, let's multiply these two numbers together first here. 1.7 times 10 to the minus 3 kilograms times VF, 5.2 times 10 to the 4 squared. This gives me the kinetic energy at the end of the problem, but we know that the kinetic energy at the end of the problem is equal to the potential energy at the beginning of the problem. If I have 2.3 times 10 to the 6 joules of kinetic energy at the end of the problem, then how much potential did I have at the beginning of the problem? Same amount, right? Then how much potential did I lose? Same amount. So this time we did have to multiply some numbers together to get the final kinetic energy, but we didn't have to do anything on the left-hand side with QV because we were simply looking for the initial potential energy, therefore how much we lost. Okay? That kind of makes sense? Yes or no? All right, I do want to do another example with this. This is on page 572. Notice our plates are vertical this time, and our charge is going to be moving horizontally. That makes no difference. Okay, we think of a car going down a hill. We don't have to have a charge going down. Okay, a charge going across can work exactly the same way as a car going down a hill. Gravitational fields always point down. Electric fields can point whatever way. But we still think of it as the car going down the hill. Here we've got a positive charge that's at rest, I believe. Yeah, it's placed at the positive plate, then it's released, and it accelerates. So it speeds up as it goes to the left here. Because it speeds up, a charged particle speeds up, we do conservation of energy, EI equals EF. The initial energy, well, if a car was going down a hill, the initial energy would be potential. At the bottom of the hill, the car would have kinetic, 1/2 mv squared. Let's sub in QV for mgh, and now let's put some numbers in. We know what the charge is here. 2.6 times 10 to the minus 12 coulombs times the initial potential, 2 times 10 to the 3 volts. And we know what the mass is. It's 3 times 10 to the minus 15 times v squared. So in those last two questions we did, we didn't have to worry about QV because we either had its value or we had the value of kinetic energy and we were trying to find EP. Here, we don't have the value of EP. If you did, plug it in here again. We don't, so we got to multiply the two numbers together to get it. Let's see what we get when we do this here. I'm going to pull this up on the calculator so that we can make sure that we're all doing okay with this. 2.6 times 10 to the minus 12 times 2 times 10 to the 3. Let's multiply that by 2 to get rid of the half. Let's divide it by 3 times 10 to the minus 15. And then let's square root that. You get 1.87 or 1.9 times 10 to the 3, I think it was. Yeah, 10 to the 3 meters per second. Is that okay? If I gave you the question that said, here's the height of the hill, what's the speed of the car when it reaches the bottom of the hill, then every single one of you would have gotten that correct, unless you made a silly mistake. You all know what you're doing for that. So let's all get this one right too. Okay? Let's try these two questions, please, at your desks. We'll go over them in about 6 or 7 minutes once you've had a chance to work on them. Put up your hand and ask me questions as I'm walking around, okay? All right, everyone, let's take a look, please, at question number 2. It says a charge of minus 6.00 times 10 to the negative 6 coulombs. That negative is important sometimes, but it's not important in an equation. We never put the negative sign of a charge into an equation. For us, okay, we want negatives in an equation to mean direction. That doesn't mean direction. It may be helpful in determining which way it's going or whatever, but not in the equation itself. So we got a charge that's 6.0 times 10 to the negative 6. It gains this much kinetic energy as it accelerates between the two plates. It's accelerating. It's speeding up. And that means it's like a car going down the hill, speeding up, accelerating. What's the potential difference between the two plates? It's like saying, what's the height? What's the height of the hill? Let's say EI equals EF. If the car is going down the hill, it starts off with potential energy. At the bottom of the hill, it has kinetic energy. Now, we're going to replace mgh again with QV, because we're not really talking about a car, even though we see it that way. QV equals 1/2 mv squared. Now, we know what the charge is. It's 6.00 times 10 to the negative 6 coulombs. Let's find VI. 1/2 mv squared. We know what the value of the we don't know what the value of the mass is, nor do we know what the value of the final speed is, but we know that it gains this much kinetic energy. So at the end of the problem, it must have 3.20 times 10 to the negative 4 joules of kinetic energy. Why bother trying to multiply 1/2 by m times v squared if we already have 1/2 mv squared? It's kinetic energy already. Let's solve for VI then. When we do, that's a big V, by the way, a capital V, we get 53.3 volts. Now, technically, in this question, what are they asking for? Potential difference. Technically, what have we found? Not potential difference. We found potential, the initial potential. But if the initial potential is 53.3 and the final potential is 0, then what's the potential difference? 53.3. So by getting the initial potential, we've got the change in potential or the potential difference as well. Right? Does that feel okay? All right, I'd like to take a look at a couple of multiple choice questions that people in the past have always struggled with leading up to this test. People in the past have always come to me the day before the test or the morning of the test. Mr. Dickie, can you help me with number 56 and 57? They're really hard questions. My response to them is, yes, I can help you with it. Yes, you're right. They are really hard questions. So what I'd like to do right now is do them in class. I'll give you about 6 minutes to work on them in class. See what you can do with them, and then we'll go over them as a class after that. And we'll kind of try to kill 25 birds with one stone here, okay? So 56 and 57, both based on the information that you see before that, right? All right, taking a look at question number 56 here. It says the minimum electron speed necessary to ionize the xenon atoms. Now, if you're anything like me in this question, the first time you see it, this is what I did in the first time I saw this question, I immediately thought EI equals EF. I immediately thought QV equals 1/2 mv squared. The problem is it doesn't work. We don't know what the initial potential is, and we don't know what the final speed is. So this method doesn't work for us. There's not enough information to solve it this way. So then when I saw this question for the first time, I started looking at other things, and is there something that I'm missing here in this question? Sure enough, there is. There was something that I was missing. In this question, we're told that an electron is accelerating. An electron has to be going a certain speed when it strikes the xenon atom in order to turn it into an ion. The electron has to be moving at a certain speed. We want to know what that speed is, the speed of the electron. We're told that the energy necessary to ionize a xenon atom is 12.1 electron volts. So in other words, this is the energy of the electron. The electron must have 12.1 electron volts of energy to ionize xenon. Now, if we're trying to find the speed of an electron that has this much energy, all we're going to do is say E is equal to 1/2 mv squared. If a car is traveling down the road with 2,000 joules of kinetic energy, and I ask you what its speed is, you would all say EK is equal to 1/2 mv squared. So if I say an electron is moving down the road with 12.1 electron volts of energy, what's its speed? Then you should do the same thing. Now in this question, there's a little bit more to do it because we have our kinetic energy in electron volts. We know that 1 electron volt is 1.6 times 10 to the minus 19 joules. 12.1 electron volts equals x joules. The x goes up by multiplying. The 1.6 goes up by multiplying. And x ends up equaling the product of those two numbers. 1.6 times 10 to the minus 19 by 12.1, which gives us 1.94 times 10 to the minus 18 joules. So we've got the kinetic energy now in joules. We can turn around and rearrange this equation to solve for speed, plugging in my value in joules, plugging in my mass. The mass, by the way, not of the xenon ion. The mass would be the mass of the electron. Look at the question. What is it that's moving here? Is it the xenon ion or the electron that's moving? The electron. If the electron's moving, it's going to be the one that we'll use the mass for to find the kinetic energy. Okay? So when we do that, we end up getting D. How many people got D? Okay, a few people did. How many people kind of made an educated guess on D? Okay, Riley, it's still smart. It's still a good strategy. Obviously, we want to be able to solve this question by doing the correct mathematics, right? But if we can't, we want to have other strategies to help us to get the correct answer. The answer is just about has to be D here. Riley, why'd you say the answer is D? All the other ones are faster than the speed of light. Okay, the speed of light is 3 times 10 to the 8 meters per second. It almost has to be D. All right? Make sense? All right, 57 says the electric potential difference across the electrified grids required to accelerate xenon from rest to its exit speed. Here we definitely are going to do EI equals EF. The xenon ion starts off with potential MGH, replace it with QV. It ends up with kinetic. In here we are talking about the xenon ion. So we're going to use the mass of xenon, which is not 9.11 times 10 to the minus 31. I think it was 2.18? 2.18 times 10 to the minus 25 kilograms. The charge of xenon tells me in the data there, it says Xe plus. Okay, right now, you're not familiar with that notation, but by the end of the year, you would be. Okay, right now, I would have to tell you, or I should have told you, that that's 1.6 times 10 to the minus 19 coulombs. So we've got the charge. Looking for this. We've got the exit speed. The exit speed of the xenon, it tells me, is 43 kilometers per second, or 43,000 meters per second. So we solve for VI. When we do solve for VI, I think it worked out to be C, 1.26 times 10 to the 3. Yes? Now, technically, I didn't solve for the potential difference. Technically, I solved for the initial potential. We saw this in another problem now, right? If the initial potential is 1.26 and the final is 0, then what's the change? What's the potential difference? Same thing. Same thing. How many people got that one? Okay. How many people got both of them? Good. Good. Those are tough questions. Those are tough, tough questions. Conceptually, they're not that bad, right? Conceptually, it's EK is equal to 1 half mv squared and EI equals EF. Conceptually, those are easy. Or I should say mathematically. But getting to that point, getting to the mathematics, it's sifting through this information and seeing what we got to do. That's the tough part of it. It's not easy. I'm going to give you some questions on 575 that you can work on, not right now, but that you can work on tonight at home if you want. They're not formal homework. I'm not going to check them tomorrow, but if you have questions on them, if you want to do them as practice and you have questions on them, you can feel free to come in tomorrow morning before school, after our staff meeting, or you can feel free to come in at scheduled help or lunchtime tomorrow, and I can help you out with these questions, okay? The ones that I would recommend would be page 575, number 1 to 9. They're all on this topic. Some of them are a little bit more qualitative. Some of them are a little bit more quantitative. Okay, they're all good questions. If you're able to, then see what you can do with them, and then come in tomorrow with any questions you have.